This short mini-lecture introduces polarity in molecules as a geometric sum of the individual polarities of all bonds in the molecule. Bond polarity was discussed in a previous mini-lecture, and we now know that it arises from differences in electronegativity between the atoms in a bond. The electron density in the bond is pulled towards the more electronegative element, and we indicate this with a dipole arrow that points in the direction that the electron density is being pulled. This creates a buildup of negative charge on the more electronegative element, leading to a partial negative charge or negative pole. And it also leaves behind a positive charge or positive pole on the less electronegative element, where the positive charge of the protons in the nucleus is left exposed as it is no longer completely balanced by the negative electron density cloud. When the electronegativity difference is significant enough to classify the bond as polar covalent, we note that the bond has a dipole moment due to the generation of these positive and negative poles. In a molecule with more than one dipole moment or on individual bonds, the dipoles must be geometrically added together, similarly to how vectors are added together, to determine whether the overall molecule also has an overall dipole moment. In the case of water below, which has two bond dipoles that point towards the more electronegative oxygen, the bond dipole moments are at about a 45-degree angle to each other. So in order to see how they either add together or cancel each other out, it helps to break the dipole moments into two vectors that align along two axes. So each bond dipole moment shown here has a vertical component, shown here in yellow, and a horizontal component, shown here in green. We know that the two yellow components are the same magnitude and the two green components are also the same magnitude because the two bond dipole moments are the same magnitude since they represent the same bond between oxygen and hydrogen, and because they are symmetrically oriented towards each other. Since the yellow components are pointing in opposite directions along the same axis, they essentially cancel each other out. But since the green components are pointing in the same direction along the same axis, they add together to give an overall dipole moment from left to right across the entire molecule. So, a water molecule is considered to be polar, and this is one of the reasons for why water has such interesting properties. Indicating the partial charges on the molecule would place a partial positive charge on both hydrogen atoms and a partial negative charge on the oxygen atom, which agrees with the overall net dipole moment for the molecule. Note that the individual bonds in the molecule must be polar in order for there to be any chance that the overall molecule will be polar. However, it is also possible to get a nonpolar molecule and still contain individual bonds that are polar. In the example below for carbon dioxide, the linear geometry of the molecule leads to both bond dipole moments canceling each other out as they are oriented in exactly opposite directions along the same axis. And they have the same magnitude because they come from the same type of bond, a carbon-oxygen bond. So, it is possible for a molecule to contain polar bonds and yet be overall nonpolar based on the geometry. When considering the polarity of a molecule, it is crucial to be able to visualize how the individual bond dipole moments within the molecule will combine geometrically. Some examples of how to think about the dipole moments within individual molecular geometries are given on this slide. Also, remember that in order for two dipole moments to cancel each other out, they need not only to geometrically cancel out, but they also need to be the same magnitude. So when a molecule has a lot of different elements as terminal atoms, it may be more difficult to determine how the individual dipoles will combine. Whereas when the molecule contains all the same element for the terminal atoms, this makes it easier to see how the bond dipoles will cancel out or add together. This concludes the second mini-lecture for Chapter 7, and the last of the material that will be covered on midterm number 2. Please note any questions you may have about this material and how it is utilized to solve problems in the sapling homework or end of chapter exercises for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our virtual class meetings, and during that time we will focus more on problem solving for concepts in this chapter. We will continue with sections 7.3 and 7.4 after midterm number 2, and we will be skipping the remaining sections in this chapter for this semester.